Welcome to EDU World Space.
This is chapter 21, problem number 18. We have two charges, negative Q naught and negative 4Q naught, and they are separated by a distance L. So now in the problem we're asked if, we should place a certain amount of charge in a region so that the net force on each of these charges, net force acting on these charges are zero. So we are asked where that charge would be and how much charge would we have to put in order to meet that requirement as to, the net force on negative Q naught and negative 4Q naught is going to be zero. So first of all, in order to determine, there are three options, right? It could be, the third charge could be placed to the left in this region or somewhere in between the charges and to the right of negative 4Q naught. So I'm going to quickly try and show you how it's actually not possible to have the charges either to the left of negative Q naught and to the right of negative 4Q naught. First of all, let's look at the force that, let's say, negative 4Q naught exerts on negative Q naught. Since they have the same sign, it'll be repelling, right? So likewise, negative Q naught applies the same amount of force on negative 4Q, pushing it away, right? So assume that we put a third charge somewhere here, and then if we put that charge somewhere here, assume that it's a positive charge, okay? If it's a positive charge, there is attraction. So positive charge is going to attract negative Q naught to the left and also negative 4Q naught to the left. This does not balance out the net force acting on negative Q naught and negative 4Q naught. So that won't work, right? Now let's assume that it's going to be it is a negative charge that we put there. Okay. If it's a negative charge, it's going to push negative Q naught away from itself, but this negative charge that we put to the left of negative Q naught is actually going to push negative 4Q naught less. So still negative 4Q naught is not, the net force acting on it is not going to be equal to zero. So to speak, the same goes for the region to the right of negative 4Q naught. So that's why we're coming to the conclusion that this third charge has to be along this line that connects negative Q naught to negative 4Q naught. Okay? All right. Well, let's look at the sign of that charge. So if it's a negative sign, let's say it's somewhere between, right? Somewhere between these two charges. Let's say it's here, and we placed a negative charge. Then again, the initial, they're pushing each other. Negative Q naught is exerting this sort of force on negative 4Q naught. And this is not going to help. Having a negative charge in between is not going to help, right? It's going to push them even farther. So then, so to speak, it has to be a positive charge. It has to be positive, and it has to be between negative Q naught and negative 4Q naught, so to speak. All right. Now that we know that, let's set up our problem. Let's call Q1 negative Q naught, okay? And we have Q3, let's call this negative 4Q naught. And then we have the line that connects them, and we are placing the third charge at an arbitrary point, okay? Not halfway or anything. And we're going to call this Q2. We don't know. We're going to try to write this Q2 in terms of this Q naught that is given to us. But one thing that we know, this distance from negative Q naught to negative 4Q naught is L, correct? So let's assume that the first part, the distance from Q1 to Q2 is some arbitrary X. Then the distance from Q2 to Q3 is going to be L minus X, correct? All right. Since we know that, now let's look at the net force acting on Q1, okay? So if we're looking at the net force acting on Q1, first we have a Q2 charge, and we know to be positive. So then the positive charge is going to attract the negative charge. So the force exerted by the second charge on the first charge is going to be towards the second charge. And the force exerted by Q3 on Q1 is going to be pushing it away, right? And let's call the magnitude is going to be force exerted by the third charge on the first charge. So from the requirement, remember the net force acting on Q1 has to be 0. So let's call this F1, okay? The net force has to be equal to 0. And it consists of two forces, F21 minus F31 then has to be equal to 0. From here, F21 has to be equal to F31. Let's write down what these forces are explicitly. K, Q2, Q1 over the distance between Q1 and Q2. We called it X. So X squared equals to K, Q3, Q1 over, what is the distance between 3 and 1, right? This is the force that we're writing, so it's total L, so it's going to be L squared. Please remember we're taking the absolute value of the charges here, okay? So Q1s are going to cancel, Ks are going to cancel. From here, what we have is Q2 over X squared equals to Q3 over L squared. We're going to need this equation. Now, let's calculate the net force acting on the third charge. Let's call it F3. Let's look at the forces. Let's say the direction of the force exerted by the second charge, since it's positive, it's going to be attraction, right? So this is going to be the force exerted by the second one on the third charge. And if you're looking at the force exerted by Q1 on Q3, then it's going to be pushing it away, right? F exerted by the first one on the third one. So F3, the net force acting on the third charge, is F13 minus F23, and that has to be equal to 0. Then F13 has to be equal to F23, which means K, Q1, Q3 over the distance between 1 and 3 is L squared. F23K, Q2, Q3. The distance between the second charge and the third charge is L minus X squared. Now you can see Q3s are going to cancel, Ks are going to cancel. So from here we have Q1 over L squared equals Q2 over L minus X squared. This is the second equation that we are going to use. Okay, now I'm going on the, please mark these two equations. I'm going on the next page. So then Q2 from our first equation, Q2 equals Q3x squared over L squared. Where did this come from? It comes from this equation, okay? I'm multiplying both sides by x squared. So the x squareds are going to cancel. So Q2 is going to be equal to Q3x squared over L squared. I'm going to do the same in the second equation. Again, I'm going to isolate Q2 from here by multiplying both sides by L minus x squared. So then, again, Q2 is going to be equal to Q1 L minus x squared over L squared. So look, L squareds are going to cancel each other out. So from here, we have Q3 x squared equals Q1 L minus x squared, right? So what was Q3? These are all magnitudes, right? Q3, Q1. Q3 is, well, it was -4 Q naught, but remember we were talking about the magnitudes there, so it's -4. It's not -4 Q naught, it's 4 Q naught because that's the magnitude. And then we have, for Q1, we have Q naught, right? So for Q naught being Q3, x squared equals Q naught L minus x squared. As you can see, these Q naughts are going to cancel each other out. So if we take the square root of both sides, then we have 2x equals L minus x. Then if we add x to both sides, then we have L equals 3x, divide both sides by 3, then x equals L over 3. All right, looking at our drawing then, x equals L over 3. So this is L over 3. So we are L over 3 away from the negative Q naught. That's where we have to place the third charge to be able to find net zero force on each charges that were initially given, right? All right. And then how are we going to calculate what the value for Q2 is? Well, use either one of these equations. So this seems like this is going to be the easiest. So take Q2 equals Q3 is 4Q naught, x squared being L over 3 squared over L squared. So these L squareds are going to cancel. So we have 1 over 9, 4Q naught over 9. So this is what our Q2 should be, 4Q naught over 9. And it should be placed L over 3 away from negative Q naught charge.